Hello everyone. In this lecture, we are going to focus on reliability in pavement design. So, what is this term reliability? We would have heard this term in different contexts, right? So, reliability is usually used to say how sure are we about something or how reliable is our assumption about a particular process. It is usually associated with a process or a system. So, a process or a system will have an input, right, and one or more inputs, and there will be a process and we will have one or more outputs. So, usually when we define the process theoretically, there will be a lot of assumptions that we are making about this particular input parameter or the set of input parameters. Then we go through the process. So, for the considered input parameters, we will be obtaining some output. But usually what we observe is that these input parameters are not those specifically that we have considered, but due to the natural randomness associated with any process, there is going to be a lot of variability in these input parameters. Hence, the output that we get is not going to be the same one that we had got before, but it is going to vary because of the variability in all these input parameters. So, considering this scenario, how sure are we about our output, right? That is kind of defined by this term reliability. So, since I said this term has lot of definitions, lot of interpretations, let me formally introduce what reliability is to you. So, this is the outline of this lecture. So, in this particular lecture, I will be focusing on the overview of reliability. We will define what reliability is, how it is essential or how it is important in pavement design process, and how it is considered in IRC 37. In the next lecture, I will talk about how reliability is considered in AASHTO 1993 design procedure, because this particular design procedure starts with assuming a reliability level. So, how is it considered in AASHTO 1993? Then we will talk about reliability in AASHTO 2004, or which is commonly called as the MEPDG design procedure, right. Then there are certain other reliability approaches wherein we can have advanced considerations for all the variabilities that we observe, especially with respect to input parameters. So, we will see some of those reliability approaches also, and then we will summarize. So, this is the outline for this overall topic on reliability, and as I mentioned, in this specific lecture we are going to talk about the overview of reliability, right. So, now what is this reliability? As I said, most phenomena in this world will have some degree of uncertainty, right. We are not exactly sure what we are going to get. Let us say we are performing a test, right. The test temperature is specified to be 25 degrees Celsius. Let me say for example, right. How sure are we that this 25 degrees Celsius is exactly going to be maintained throughout my test? There might be slight variations in atmospheric conditions. So, because of that, let us say that equipment is equipped with some temperature control device. So, it will adjust the temperature to meet the 25. So, there may be a few instances of time that this temperature may be 24.9 degrees Celsius or 25.2 degrees Celsius. Right. So, there is some variability around this value that I have considered. That is why if you see, most test procedures will specify 25 plus or minus 0.5 degrees Celsius, right. So, they consider in for the variability. Okay. Let us take another example which is more related to pavement design. Let us say that I am designing my pavement and it is supposed to take 10 million standard axle repetitions of my standard axle load. So, we colloquially say it as 10 MSA, right. So, let us say I design my pavement to carry a load capacity of 10 MSA. Now, will it carry exactly 10 MSA, right. So, when I have the first repetition after this 10 MSA is exhausted, will it fail, right. We will define what failure is again, but will it fail, right. So, let us say there is again defining what failure is going to be slightly complicated for pavement, but let us say there is some definite, let us say we are able to define some definite point of failure for a pavement system. So if I can define something like that, and if I am able to capture the number of load repetitions at which it is going to fail, and we can certainly say that it may not be exactly 10 MSA always, right, it is going to be slightly less or slightly more. So why do we see that variability? So it can fail at 9 MSA, or it can fail at 11 MSA or something less or more. So why do we have this variability? Right now, if we recollect the pavement construction process, so we have a design, like I said earlier, we have lot of input parameters which we use in design. So let us say we have a modulus, we have thickness, Poisson's ratio, then we have traffic parameters, so many input parameters. When we are designing, we give one single point value to all these measurements, right, and based on that I am computing my critical strain values, and for those critical strain values I am computing the number of repetitions to failure. So what if there is some variation in one of those input parameters? So obviously the critical strain is going to vary, and so the number of repetitions to failure, right. So now there are lot of input parameters, each input parameter can vary over a range. So my critical strains are also going to vary over a range, and my number of repetitions to failure, which is my output, is also now going to vary over a range, right. So every process in this world has lot of uncertainty, and the more the number of parameters that are involved and more higher the degree of uncertainty with each of it, the lower is our ability to correctly predict the point of failure, right. So that is why reliability is usually defined in terms of the probability of failure, right. So we know what is the probability of failure, and if I can say that as P of f, reliability, which is nothing but 1 minus the probability of failure. So if a system has a higher probability to fail, then it is considered to have a lower level of reliability. So if I have designed a process which has only 1% as the probability of failure, so I have considered all the scenarios, let us say, and I am able to say that 99% I am sure that it will deliver the desired performance, right. Then my probability of failure is only 1%, my reliability is going to be 99%. So when I am very sure that the probability of failure is low, right, I am saying here that I am very sure, that is what I call as reliability. When my probability of failure is less, my reliability level is high, okay, and vice versa, right. So that is why we say higher the probability of failure, lower the reliability, and vice versa. Now let's look at some standard definitions as to how this reliability is defined. So if I look into Oxford's Learner's Dictionary, this is what is the meaning that is associated with the term reliability, right. It is the quality of being able to be trusted to do what somebody wants or needs you to do, right. So that is what this means. So again, if I translate it to the same pavement design example, I design a pavement, I want it to operate without any failure for up to 10 MSA load repetitions. How much is it going to meet that promise, right? That is what is reliability. So if I am 100% sure that it will carry 10 MSA, then my reliability of that particular pavement design is 100%. But if I am only 50% sure, I know that there is going to be lot of variability in my input parameters, I know that there is going to be lot of variability in the construction process, so thickness, modulus, everything is going to vary around, then I am not very sure that it is going to carry the 10 MSA or not. In that case, my reliability level lowers, right. So it is the quality of being able to be trusted to do, how much trust I have on that particular pavement design process, so that it will carry that particular load. So AASHTO has specifically given, again AASHTO has many definitions. When I am talking about the AASHTO 1993 design procedure, I will go through all those definitions, but I have given one relevant definition to motivate reliability for the pavement design perspective. The reliability of the pavement design performance process, right. So it is design, which is associated with the performance. We are expecting some degree of performance from this particular system. The reliability of pavement design performance process is the probability that a pavement section designed using the process will perform satisfactorily over the traffic and environmental conditions for the design period. There are a lot of terms that we have to look into critically in this particular definition. First is probability. So, we are saying what is the probability, right. So, that is the first thing, that a pavement section designed using the process. So, there is a particular design procedure that is being followed here. So, it could be a standard procedure like IRC 37 or AASHTO 1993 or the recent MEPDG version of AASHTO. So, there could be some particular design procedure. So, using a particular design procedure, it will perform satisfactorily. So, what is this satisfactorily? For what conditions are we designing the pavement? Let us say my concern is to limit the rutting to 20 mm. Let us say I want to limit, let me be specific, total rutting to 20 mm, and I want to limit fatigue cracking to 20%. Let us say this is what I consider as satisfactory performance, and I am going to use the design process to meet these criteria, right. So, this is what I consider during my design process, and this is going to be my satisfactory level. So, then it should meet these conditions over the traffic and environmental conditions. Again, we have different traffic on the road, we have different environmental conditions for the geographic location. So, considering all this, it should perform satisfactorily over the design period. So, we all know what design period is. So, the period for which we consider that it is going to deliver this performance, right. So, it is the probability that it will do all these things. So, that is what we call as reliability, right. Now, if I have to simply put this definition of AASHTO in one sentence, it is a probabilistic assurance of performance over its design life, right. So, we are associating a probability to it, we cannot say that we are 100% sure, right. So, we always associate a probability to our design predictions. So, probabilistic assurance of performance, again this performance is what we assume during our design procedure over its design life. Now, let us say there are a number of parameters which we use for pavement design. So, let us typically consider our IRC 37 design procedure. Again, we have different layers, right. So, for each layer we specify a modulus value, we have a thickness value, and then we have a traffic load which is acting on it. So, we have a load parameter, and then we also have the tire pressure of this, and then we have number of repetitions of this load value, right. These are some parameters which we typically use to compute our critical strain values, right. So, in IRC 37 design procedure, if you look at it, and we also use a Poisson's ratio value, right. So, these are the input parameters. Now, how much is the variability associated with all these input parameters, right. We all know that all of these input parameters will have certain degree of variability. These variability can be of different degrees. Let us consider 1 kilometer stretch of a pavement. Let us say this is 1 kilometer. So, at a given instance of time t1, let us say I am measuring all these parameters at some 5 points in this 1 kilometer stretch. So, I am going to measure the all the input parameters, modulus, thickness. Let us say I am measuring Poisson's ratio also, and what is the load that is acting on the pavement for a given vehicle repetition, and what is the tire pressure. I am going to measure all these things at these 5 points for a given axle. So, most probably the vehicle load and the tire pressure might remain more or less identical. But if I am going to measure these 3 parameters, which are the modulus, thickness and Poisson's ratio, we know that it is not going to be exactly the same in all these 5 locations. So, as I said, let us say we have a 400 mm thickness specified for one layer, it is going to vary some units this side and some units on this side, right. So, there is going to be a spatial variation in all these parameters at a given instance of time. Then there is also variation in these parameters with time, right. As the pavement ages, let us say we take the bituminous layer, as the pavement ages, the binder is going to become stiff. There are a lot of phenomena that are going to happen in the bituminous layer. So, it is going to become stiff and the modulus value is going to increase. So, if I measure at this particular point at different instances of time, right, the modulus value is going to increase. So, these are 2 different factors which contribute to variability. Also, we have seen the effect of climate on all these material properties. So, we have seen that if I take a particular year, these values are not going to be constant over a year because of the influences of, let us say, if you take a bituminous layer, the temperature parameters, or if you take a granular layer, the soil moisture related parameters, the modulus value is also going to vary, right. So, there are a number of parameters which contribute to variability in all these input parameters, and these variabilities are associated with multiple outcomes without any pattern. There is no specific, let us say if it is a variation like this, then we classify it under seasonal variation, right. But if I am going to measure it at these points, these 5 points, it is going to be random, right. There is no specific pattern that it is going to increase from these 5 different points, provided the construction process is uniform over the entire 1 kilometer stretch, right. So, all parameters used for design will have some inherent variability without any pattern and some pattern based variability over the design period, right. Hence, the design life or the performance of the pavement in its design life is not deterministic. We cannot associate one single value to all this variability. It is going to be probabilistic, right. It can be only said with a certain degree of probability, and we cannot 100% certainly say that it is going to be this particular outcome for this process. So, that is what is the concept of reliability that we are using for pavement design. Now, how do the traditional design approaches consider this kind of variability, right? It is usually done through a parameter called factor of safety. So, many times when we design, we see what is the allowable, let us say we require a particular strength, we see what is the required strength for our case, multiply by a factor of safety and say that we need a material which is twice more strong than what is actually required at my location. So, I am able to factor in all these variabilities, and I am sure that if I am using a higher factor of safety value, then the system is not going to fail in my expected design life, right. So, we account for these kind of variabilities by using a factor of safety parameter. So, for a pavement, how is this factor of safety defined? It is the expected allowable number of standard axle repetitions to the expected number of applied standard axle repetitions. So, this is my allowable or the maximum value that my material can take, and this is the expected or which I am going to observe in my case, right. So, I divide this, I get a parameter called a factor of safety, and this is always greater, it should be always greater than 1, right. If we want a system to be, like if you want to be more sure that it should not fail at all, then we resort to using a higher factor of safety value. But again, this factor of safety is only a number, right. We do not know what factor of safety should be used. So, for let us say for a pavement of high importance or where you think that the variability is large, we tend to use a higher factor of safety value, and wherein we are sure that there is not much of variability, we tend to use a lower value. but there is no specific guidance as to what factor of safety should be always used, and there is no guarantee that if we use this particular factor of safety, then this pavement is not going to fail at all. It is only an adjustment which we make, and that number we allocate there is based on our previous experiences, right. So, intuitively we feel that if it is of a good quality construction and if it is designed considering many parameters, we tend to resort a lower factor of safety, right. It is only intuitively done, and there is no guarantee that the pavement will not fail if you use this particular factor of safety. So, this factor of safety based approaches has a lot of limitations in it. So, that is why probabilistic analysis are resorted to, wherein the actual variation in parameters are considered and it is inbuilt into the design process itself. So, if we take a particular input parameter, what is the variability that is experienced by this input parameter, it is quantified, and that those values are actually taken into the design process. So, we can be more certain that the probability of failure will be less when the actual variation of material parameters are incorporated into the design process. So, this reliability uses the methods of probability and statistics. So, what is this probability? We use probability to compute the likelihood of pavement failure. What is the probability that pavement will fail? So, to compute that, we use the basics of probability and we use statistics to arrive at mathematical quantification of uncertainty. So, this reliability is built on the concepts of probability and statistics. Now, let us see what are the factors which lead to variability in a design process. So, to illustrate that, I am considering this example from this particular reference. So, it is for fatigue cracking. So, let us say that we want to predict fatigue cracking and consider it for our design process. Now, this again involves a number of input parameters as we have been discussing. It involves thickness, it involves modulus and Poisson's ratio, temperature and moisture, and the variation in modulus because of these parameters. Then there are a number of traffic related parameters, the load, frequency, lane distribution factor, the directional distribution factor, number of axles per truck class, which is an approximation that we will be using. I will, when I am explaining AASHTO, I will talk more about this. The axle load spectrum per truck class, or in fact you would have discussed all these things in the previous lecture on traffic. Hourly distribution factor, AADT, monthly distribution factor, traffic wander, truck type distribution factor, growth factor. So, there are a number of input parameters which we consider when we do a detailed design with the traffic input parameters. Now, considering all these, so you can see there are uncertainties in all these input parameters. Now, considering all these parameters, the mean value of the variables are used, right. So, if I have a thickness, let us say I am measuring thickness at 10 points, I get all the 10 values, I take the mean value and I use it for my design process, right. And the flexible pavement analysis is deterministic, right. For a given set of input conditions, we get one critical strain value at the bottom of bituminous layer and one critical strain value at the top of subgrade for a given set of input parameters. So, it is a deterministic analysis. Now, I take that strain value and I input it into my transfer function. Okay. So, we in some cases we will also need information on modulus and Poisson's ratio for the transfer function as well. Now, from this we are computing the fatigue life, and from that the damage index is computed for the mean input value. So, all my inputs are one single measurements, though I have a range over which each of these parameters can vary. So, for that input parameter we are computing the damage index and computing the fatigue cracking. So, this is said to be at 50% reliability because we are using the mean value. So, whenever we perform a design wherein we use the mean value and carry out the design, our reliability is only 50% sure, 50%, that is we are 50% sure that it will not fail, right. but if we want it for any other reliability, then it has to be corrected. So, it is the fatigue cracking at 50% reliability plus standard error into standard normal deviate. So, what is the standard normal deviate? I will show you in some time. Okay, so this is how the reliability is considered, and it is accounted for other values apart from the mean input parameter. 2-3 lectures down, we will carry out an analysis wherein we will consider the actual variability in the input parameters and see how we are able to define the reliability for that particular case. So, now let us spend some time in discussing about the factors which lead to variability and the magnitude of variation that we typically observe in each of these parameters. So, one can ask, right, so what is the big deal about each of these parameters? Some parameters will might not vary that much. So, is it going to have a big impact on my design, right? So, for that we need to know what is the degree of variability, or I could simply say it as what is the standard deviation if I collect a set of values for each of these parameters. So, based on that we can say how much is the variability associated with the particular input parameter. So, if we look at, let us say I am starting from traffic, we have axle group, the load, tire pressures and even the types of tires, axle spacing, the speed in which they travel, number of repetitions. So, like that many parameters associated with traffic. Then we also have environment related factors, we have moisture, we have radiation, we have temperature. So, these things are going to vary in a random manner. So, we have already seen what is the degree of influence exerted by each of these parameters on our modulus values. So, once the modulus value changes, obviously the critical strains are going to change and my allowable number of repetitions. Then we have a structure. So, again as we said, the type of layer, the type of material that we use, thickness, the properties of each layer, again it is going to vary, and the subgrade type and properties and all those things, right. Then we also have the construction practice wherein all these design parameters are translated to field. So, we have the time during which it is constructed, the methodology using which it is constructed. If I am going to use a very precise, let us say I am laying an asphalt layer, if I am using a paving machine which has precise control over the thickness and other things, then my layer is going to be more or less uniform. On the other hand, if I am resorting to other methods to lay, or wherein I am not sure about the thickness that is being laid, I do not have any automated means, then there is going to be lot of variability, right. So, the construction methods also will play a big role, the as-built quality of pavement that we can observe here, and the variance that is associated with the process. Similarly, if I am doing some maintenance operation on this, what are the treatments I am giving to a particular location, at what time I am providing those treatments, what are the methods which I use, and what is the quality of those treatments, right. So, these things are also going to vary. So, my measure of deterioration of a pavement, let us say this is the condition of a new pavement which is in its as-built state. If this is the serviceability of that pavement, it is going to deteriorate with age, right. How it deteriorates? It can deteriorate like this or like this or like this. So, the manner in which the pavement deteriorates is the combined influence of all these parameters which are discussed here and the manner in which they vary. It is not only the variability of thickness, but to what extent thickness varies or to what extent the modulus varies, which is usually quantified by its standard deviation, right. So, the measure of serviceability is the combined influence of all these input parameters which are given here. So, if I have to specifically separate them into individual parameters, it could be given something like this. Okay, do not worry about it, it is not that complicated. Once when you understand what each of these boxes are, you will be able to understand. It is nothing but a summary of all the variabilities that I have been discussing so far. So, if you look at pavement analysis, this is our crux, right. It is going to depend on a number of parameters. So, what does it depend on? it is variability of surface layer. So, I have a mean value and I have a standard deviation if I am going to collect a number of points at which I can measure H1. Similarly, I have variability of base layer which I call it as H2. So, I am going to quantify that using a mean value and a standard deviation value. Similarly, I have variability of elastic layer modulus of surface layer. So, E1 value, again for each of it I will be able to associate a mean and standard deviation. Now, if I use a fatigue equation, then we have some constants in the fatigue equation that you are aware of. So, value of the constant K1F, again if you have another constant it is K2F, right. Then it is the variability of traffic growth rate R, variability of vehicle damage factor VDF, we all know what VDF is, variability of lateral distribution factor, what is the present traffic that is observed at the given moment and the design period that is considered, right. And we also have variability of modulus of base layer E2, of subgrade E3, again Poisson's ratio of surface layer, Poisson's ratio of base layer, Poisson's ratio of subgrade. Then we also have the wheel spacing, right. We have, if you take a dual axle, we have wheels. So, what is the spacing of these wheels, and even the axle spacing you can consider here, variability of tire pressure. If you use the rutting equation, then we have two constants again K1 and K2 in the rutting equation. So, what are the constants for the rutting equation, right. So, if you typically consider a design methodology something similar to IRC, even in that kind of a design methodology, we will have these many number of parameters and each of them will have a mean value and a standard deviation, which means it is not one point measurement like this, but it is going to be a measurement over a range, right. It can vary anywhere between the range, right. Now, for this I am going to compute the, so considering all this variability, if I input it in pavement analysis, there is going to be variation in fatigue strain, variation in rutting strain. So, this epsilon value along with the modulus and the constants, it is going to influence my fatigue equation and therefore, my fatigue life is going to vary. Similarly, all these parameters along with the variation in strain is going to influence my rutting equation. So, I am going to have a variation in rutting life. So, later I will show you some plots wherein you can see that if I use the probability based approach and if I consider the variability of all these input parameters, my output is not going to be one life that I will be getting for my pavement system, but my pavement life can vary over a range as in the case of these input parameters, right. I will show you some plots. I will refrain from drawing a distribution at this point of time. Let me show you some data and then we will see how this varies. Then we have again the expected traffic, right, what you can expect on your pavement. This also varies depending on the growth rate, VDF, lateral distribution factor and all those things, right. Now, considering the variation of traffic, variation of fatigue life and variation of rutting life, we will be able to define the reliability for that particular pavement system. So, that is what we get as reliability for the pavement design, right. So, if you want to carry out a very simplistic analysis, still we will have these many parameters and the variability associated with all these parameters. So, what is the outcome, right? What will happen because of the variability of all these input parameters? Let us say I have a pavement, this is my time, this is my assumed desirable design life, okay. Let us say I design it for 10 years, let me take a specific example for the sake of discussion. I design it for 10 years. Will my pavement serve exactly for 10 years as I said earlier? It may not be, right. So, it will be around this. So, it is usually approximated with the normal distribution. So, it will have a variation like this over this 10 years. But in realistic, this is our desirable case. In reality, what we are going to observe in the pavement is something like this solid line which you can see here. There are going to be some pavements which will exhibit premature failures and some of them may work around the design life also, right. So, it might happen that we can have pavements which fail much earlier and some pavements which meet the design life for which they were designed. So, why do these pavements undergo premature failure? Because the assumed conditions in our design is not same as the conditions which were translated into execution, or we could have failed to consider some of the variability in the material properties during the design procedure, right. So, if we are able to consider all those variabilities, we may be able to minimize the premature failures or make better approximations in the design process.